Hello students, in the last class we have seen the concept regarding the real numbers, the first chapter of your math class 10th CBSE NCERT book. So we have seen all the concepts like in the previous class. In order to understand the concept, similarly I have prepared a note for exercise. This is the problem 1. So what is it saying? The problem 1 is saying that using Euclid's division algorithm, find HCF of 135 and 225 using Euclid's division algorithm only. So what did the algorithm said? That since 225, it is already over here, but still we are doing it for better understanding. Since 225 is greater than 135, so applying Euclid's lemma division, 135 being smaller number should divide 225 being a greater number. It goes 1 times 35, we will get a remainder 90. Okay, now again we will divide 135, the remainder becomes the divisor. This is the remainder. Now this becomes divisor, and this is dividend. The divisor becomes a dividend. So now 90 goes 1 times, 90 1 90, again we'll get a remainder 45. This is the remainder 45. Step 3, again the remainder becomes the divisor and divisor becomes the dividend. Applying it goes the lemma division goes in step 3. Since this is not equal to the remainder, it will be applied. This means this repetitive step will be followed until the remainder becomes 0. Here remainder is not equal to 0. Here also remainder is not equal to 0. Now coming to this step, 45 2s are 90. Here the remainder becomes 0. So 45 is our HCF. That's how we will apply the lemma Euclid's division algorithm. Okay, and we'll find our answer. So the HCF of 135 and 225 is 45. Moving on to the next problem. Problem 2 says any positive odd integer, remember this thing. This is asking for positive odd integer is of the form 6q plus 1, 6q plus 3 or 6q plus 5. Okay, we'll have to prove that any positive odd integer, remember that any positive odd integer should be of the form of 6q plus 1, 6q plus 3 or 6q plus 5. So how do we approach this problem? So we will start like this. Let a be any positive integer. Okay, there's some problem with my pen. I don't know what is the problem, so just please bear with me. So let a be any positive integer, and what is a is equal to bq plus r. That was our Euclid's lemma division, where a was what? A is our dividend, b is our divisor, q is our quotient, and r is our remainder. Okay, so let a be any positive integer and b, since we have to prove that it should be in the multiple of 6q plus 1, q is our quotient and 6 is our divisor. So let b is equal to 6, b is equal to 6. Okay, and a be any positive integer. So applying Euclid's lemma division, a will be equal to b into, not b but 6 into q plus r. R is our remainder. When the remainder is 0, r is equal to 0, what happens? A becomes is equal to 6q. Is it even or odd? This is even. Okay, this particular statement is even. Now condition number 2, this is one condition. Condition number 2 says if r is equal to 1, what happens? A is equal to 6q plus 1. Is it even or odd? How do we find it? Since 6 is the multiple of 2, which should be even, but if we are adding 1, it becomes odd. So this is odd. Condition number 3, when r is equal to, I am writing over here 0, but it should be written over, it should be 1. So condition number 3, when r is equal to 2, a will be equal to 6q plus 2. Again 2 is a common over here, 2, 3q plus 1. So this is a multiple of 2, this is a multiple of 2. This particular statement becomes even. So condition 1 is met. So let's go for condition number 4. Condition number 4 says r should be equal to 3. Let's take r is equal to 3. So here again the expression will become a is equal to 6q plus 3. Let's take the 3 is the common over here, 2q plus 1 remains over here. So what do we see over here? That the inside of this bracket is already an odd number and it is multiplied by odd. This becomes, the whole expression becomes odd. Okay, so this is an odd expression. Let's take condition number 5. Condition number 5 says r is equal to 4. So as per condition number 5, when r is equal to 4, so the expression becomes 6q, a is equal to 6q plus 4. So here we will take common 2, it becomes 3q plus 2. So the inside of the bracket, again we'll see that the inside of the bracket is 3q plus 2. Whatever be the multiplication of this thing, if we'll add 2 in this, it might be even or odd, but since the outside multiplier is an even 2, this becomes, the whole expression becomes even. So moving ahead, let's go for condition number 5, which is r should be equal to 5. Condition number, not 5 but 6. Condition number 6, we can see that r should be equal to 5. When the remainder becomes 5, what will be the expression? That is a is equal to 6q plus 5. So this will always be even since the multiplier is 6, but the whole expression, when we are adding 5 into it, the whole expression becomes odd. So because adding any odd number to the even number, the whole number becomes, the total number becomes, the whole expression becomes odd. So in these conditions, we can see over here from condition 1 to condition 6, when r is equal to, no sorry, condition 1 is from condition 1 to condition 6, we can see that r is equal to 0, the expression becomes 6 is, a is equal to 6q, which is an even number, which is even number. Okay, but when the condition r is equal to 1, the expressions become a is equal to 6q plus 1, which is an odd number. When r is equal to 3, the conditions become, the expressions become 6q plus 3, which is again an odd number. When in the sixth condition, where r is equal to 5, the whole expressions become 6q plus 5, which is an odd number. So hence proved that, so here we can see that for any positive odd integer, remember positive but odd integer, it should be of the form 6q plus 1, 6q plus 3 and 6q plus 5. Hence proven, when remainder is equal to r is equal to 1, the whole expression become 6q plus 1, which is odd. When remainder r is equal to 3, the whole expressions become 6q plus 3, that is odd, that positive odd integer a. And the whole when remainder is r is equal to 5, the a is that any positive integer a is 6q plus 5, which is odd. So since a is odd, it cannot be 6q or 6q plus 2 or 6q plus 4. Hence proved. This is our second problem. Okay, we have understood it perfectly. Moving on to the third problem, that any army contingent, this is an army contingent, okay, of 616 members, the numbers, total numbers are 616, to march behind a band of 32 members. What is the maximum number of columns? Maximum number of columns, again the total number is 616 army contingent, and it should march behind the band of 32 members. So coming to this problem, so how can we approach this problem? We can definitely approach this problem by using Euclid's lemma division. That means finding out the HCF, the highest common factor. So we will divide 616, being the greater number, we will divide 616 by 32. So we will see how many times then we can multiply 32. 32 should be multiplied 19 times. We will get the result as 608. The remainder will be 8 over here. We will proceed to the next step where the remainder becomes the divisor and the divisor becomes the dividend. Okay, so we'll divide 32 by 8, which will be divided perfectly, leaving remainder as 0. 0 is the remainder over here. So our last divisor will become the HCF. So they can march in a column of maximum of 8 columns. They can definitely march within a maximum of 8 columns. So that's how we approach the problem, by using Euclid's lemma division to find the HCF of the given number 616 and 32. Okay, which resulted into 8 being the HCF, the highest common factor between 32 and 616. That means the army contingent of 616 members can march in a maximum of 8 columns behind a band of 32 members. So this is our results. Here we end the exercise 1.1. We will do the exercise 1.2 in the next class. We will try to keep the classes as short as possible so that you can learn maximum in minimum time. Your screen time should not be beyond your limit. That is my approach. So thank you very much. In the next class, we'll try to solve problems of exercise 1.2 of the same chapter, real numbers. Thank you.